Hello, welcome to the lecture on reconstruction of sampled signals. This lecture is going to focus on how we can obtain a continuous time signal from a sampled discrete time or digital signal and what the issues you have to be aware of with regard to this are. So when you have sampled signals and we want to go to continuous time signals, the main aim is digital to analog conversion. That is, you typically have an array of digital signals which has either been stored digitally or has been received after processing or transmission. As an example, if you take your speech signal, which when you speak over the phone, the speech is converted to a digital form, and then when your friend picks up your call and listens, it is converted back from the numbers, digital numbers, to analog form. Now when it is compressed, you must remember that xn is known only at integer values. That is, since xn is known only at integer values, so this becomes very important because we have no idea how to interpolate in between. Well, now we can try some things, okay? We can use some information. For example, that this came from a speech signal, this went through this processing, and that kind of information can be used in order to fill in the missing gaps. But what is that precise information? As an example, one thing we have been looking at as part of this chapter is whether the signal is band limited, or whether you know the sampling rate, or the whether it was sampled once every t seconds or every at the rate of fs samples per second or things like that, or was it some other type of signal, and all these kinds of questions will start to pop up. We are going to see some assumptions on how we can get over these issues. So the focus is on reconstructing the continuous time waveform. So how do we reconstruct the continuous time waveform? We will take this example of this 4-point sequence which we had earlier. As you can see, we have 4 non-zero values. Of course there could be more, but I am looking only at these 4. Now there are certain things. So for example, we don't know what is between 0 and 1, 1 and 2, 2 and 3. So let us try to make some educated guesses. The first is a sample and hold. That is, remember that at x is equal to 0 it is 1. So when it is 1, think of this as a the output voltage from the circuit is held constant. Okay, this is sample and hold. We are going to keep it at 1 or 1.2. At time n is equal to 1, the value jumps to 2.3 and it stays at 2.3. One issue which you will face with this kind of a reconstruction is that it is going to become jagged, because you are always going to have this step-like structure to your reconstruction, and it's not going to be the smooth curve that you thought it was. As an example, if this was obtained from a speech signal, you typically consider it to be a waveform which is more natural as opposed to having these kinds of jagged structures. So that is something which leads to issues, and this is not, most of the time this is not a faithful representation. There are exceptions, especially when we deal with synthetic signals which change only in ticks. For example, let's say something like stock prices. Stock prices change in intervals which are more discrete, but for natural signals we expect something a little better. The next refinement that we can think of is linear interpolation. This makes complete intuitive sense, because if you don't know the value between 2 points, for example, you know what it is at 0, you know what it is at 1, interpolating or drawing a straight line between them may be a good idea. And in fact, if you have enough number of samples, even the sample and hold and the linear interpolation will give you a very good approximation of the actual continuous time signal that you had. Nevertheless, this also seems to have issues at the points where there are sharp turns. For example, if you notice at this point, there seems to be an abrupt kind of change in the slope. Similarly over here, and these are typically not representative of natural signals. You would typically have something which is a little more gradual changing, right? Okay, fine, but then if your signal is like this, there's nothing that can be done. This is what it is. But if I now give you the additional information that this signal was obtained by sampling a band limited signal, okay, then we know that if I have sampled this from a band limited signal and I have honored the Nyquist criterion, then there is a unique band limited continuous time signal that can be reproduced from this. So that is what we're going to call the correct reconstruction. Excuse me. So once again, I want to emphasize, if I tell you that this particular xn has been obtained by sampling a band limited signal, and that too by honoring the Nyquist criterion, then there is a unique continuous time signal that would give you this xn, and no other continuous time signal which will give you this xn. If that is the case, then we should be able to go back. So to give you a pictorial perspective, this is like telling, you have a wheel and the wheel is rotating and you have enough samples of the wheel to reconstruct the rotation. This is just a more advanced version of the same problem. So to get the answer to our question on how to reconstruct, remember that this is what happened in the frequency domain when we sampled. It is very instructive. So if you assume that this triangle is the Fourier transform of the signal that we originally sampled, it was a band limited signal. It can be either shape, not necessarily a triangle, but let's say this is it. If my sampling rate fs, which is 1 upon t, in other words, if I sample by taking one symbol every t seconds or fs symbols every second, if that exceeds 2w, then the copies that are produced, remember, sampling is multiplication by impulse train in the time domain, convolution with an impulse train in the frequency domain, which leads to samples. If these samples are separated by more than twice w, then you can potentially get back your original signal. How? Notice that your original signal is hidden inside here in plain sight, because this particular range, which is this triangle, was the original signal. By sampling, you added copies, but these copies did not clobber this original signal. They did not cause any damage. So there must be a way to go back. What is the way to go back? I just mentioned that the original signal is exactly this. So to go back to the original signal, you just need to zero in on this particular band and eliminate everything else. What is the easiest way of doing that? You know that the easiest way is to multiply it by a rectangle in the frequency domain. But of course, you know that multiplication with a rectangle in the frequency domain, which is centered about 0, is the same as low pass filtering. So in other words, what we are saying is that if you take your discrete time signal and pass it through an ideal low pass filter, you will get back the original waveform that you wanted, because all those copies disappear. Now let's actually go back and think about what we said when we did sample and hold and linear interpolation. Sample and hold and linear interpolation are also smoothing operations and are also low pass filters, if you think about them. The reason that happens is because the original signal, which has these impulses, is spiky, and that spiky signal is the one which has all these. I'm talking about the signal which has many impulses. By removing those impulses in the frequency domain, you are actually multiplying it by an ideal low pass filter, which means you will end up with only this triangle, which is the original signal that you started with, and I'm sorry, let me go back, and this is what you need to do in the time domain also. Just to re-emphasize, if your sampling rate is higher, which means that you take samples at a much higher rate. So in other words, rather than have a signal like this, you have a signal like this with more samples. If you have more samples, then you have a little bit of flexibility in designing your low pass filter, because you don't need to cram that low pass filter just at minus W and W. You can put it slightly afar from minus W to W or even wider, and you have a range of low pass filters which will give you the same original signal. When designing low pass filters for reconstruction, because the ideal low pass filter is not realizable, practical considerations will demand that you have to go out of the band a little bit so that you can accommodate even any imperfection in the filters like this. Okay, you can do things like this, but that is something which we will see later. The short story is that if you can find, or if you can make a filter which has which basically removes all these copies, you will end up with the desired signal. So the right answer, when you have been told that the signal was sampled from a band limited signal, is to use rect of f upon fs, which means multiplication by rect of f upon fs in the frequency domain, which translates to convolution with the sink of TFS in the time domain. So what is the picture that you need to have? The picture that you need to have is that you need to basically place a sink at every impulsive stick. Okay, so remember, if you imagine your discrete time signal to be a stem plot, okay, with these stems going up and down those lollipops, you have to essentially place a sink at each and then add them all up, superpose. Okay, now this is actually very important because this is actually representative of the continuous time band limited signal that was used to produce this discrete time signal. How? So remember that signals can be represented as a superposition of delta n's. Okay, that is, if you have a value at x0, if the value at 0 is x0, you can call it x0 delta n. If the value at n is equal to 1, which is what corresponds to t, is x1, then that will be plus x1 delta of n minus 1. So this is something we have seen, right? You can use impulses to represent a discrete time signal. Now each of these impulses becomes a sink. So if you see here, at x0, at 0 the value is x0, at 1 the value is x1, and incidentally there are these two little stems sitting there, and there's a sink which is the black one and the sink which is the red one. So if you have this signal which is, let's say, x0 and x1, both are, let's say, 1 and 1, what is the resulting reconstructed signal? You have to add these two sinks to get them. But when you add, notice something very interesting. At 0, the value is x0 and the contribution of the red sink is 0. This is because of the property of the sink that at every integer multiple of the argument of the sink, its value is 0, which means that at 0 the value is exactly x0, which is what the value of that impulse was. At t, which is n is equal to 1, the value is x1 and the contribution from the black impulse is 0. In other words, when you add these two impulses, the values at x0 and x1 will not be affected. Similarly, the values at every integer multiple of t will all not be affected. They are all 0. This is an important realization that you should have when you reconstruct the continuous time signal. The values at integer multiples of t will have your discrete time signal hidden inside there. They'll be exactly the same values. Let's actually add these two sinks up and see how they look. So in this animation, I'm actually changing the value of x1, and what you see is, as you change the value of x1, the value at x0 does not change. So you can see that the resulting sync, which is the red one, is actually obtained by adding the sync corresponding to x0 and the sync corresponding to x1, will alter the shape at various places. But at integer multiples of t, the values are unaltered. So I'll just go through it once again. So if you look at it again, as you change x1, notice that there are some deviations over here, there's a deviations over here, and so on. But exactly at integer multiples of t, because of the properties of the sync, they do not affect the other values. So in this case, it's like delta n plus alpha delta n minus 1, where x1 is a value is alpha. You can see that at small t equal to 0, it's x0. At small t equal to capital T, it's x1, which is the value alpha. And at all other places, the 0 is being honored because of the fact that this is a sync. In between, there will be variations, but these variations are inevitable. This is the price you pay for band limitedness. Band limitedness means time unlimited, and these wavy features will continue to remain till infinity, although they become small. As a final example, you all know about rectangular windows. We've seen them, right? It's basically the sequence delta n plus delta n minus 1 plus delta n minus 2 and so on. When you reconstruct a rectangular window, you will not get a rectangular window in the continuous time. Okay? So have a look at this animation. I'll pause it for a bit. So you can see that the sequence is actually 1, 1, 1, 1, 1, and it's 0.8 over here. It's not gone to 1. You can see that if you squint your eyes and look just at these lollipops, they look like a rectangular window because all values are the same. They are all having the exact same value and they look like a flat rectangular window. But we constructed this from a band limited signal. Now, if you look at the continuous time rectangle function, it has an abrupt jump and an abrupt fall. All abrupt jumps and abrupt falls are accompanied with the presence of an infinite range of frequencies, which means that using just a band limited signal, you can never recover a continuous time rectangle from a discrete time rectangular window. That's just not possible. Nevertheless, it's still an approximation, as you can see. So I'll show you once again. So as you can see, the waveform changes while the values are being held constant at those particular locations. So this is something which you should bear in mind. So whenever you have any rectangular window, do not think that it is corresponds to a continuous time rectangular window. It's always band limited. The way to avoid making those mistakes is to always consider a sync sitting exactly on any of these stems and then adding them all up, because the basic unit of reconstructing from continuous time is a sync. Think of a sync being multiplied by the value and output and then superposed. That will always give you correct answers. So as an exercise, if I ask you to find the value of the signal, continuous time signal that this discrete time signal corresponds to at, let's say, 3t upon 2, what will you do? Yes, of course, you will have to use the sync reconstruction, but this is something I'd like you to think about. So in summary, whenever you use sync interpolation, that is going to give you the exact band limited signal that corresponds to the discrete time signal that you started with. Any other approach may give a good approximation, even a practically usable approximation, examples being sample and hold, linear interpolation, and so on. And in fact, if the sampling rate becomes very, very high, then you will find that it actually almost matches the sync interpolation. But mathematically, the only way to get back, the filter that gives you back the continuous time signal that corresponds to a sampled, the sampled values, is the sync interpolator. Thank you.